Hello, we're going to move to talking now more about CO2 and how it is carried in the blood. And then towards the middle, we're going to switch to talking about ventilation-perfusion mismatch and what that means for a normal lung. So we've talked about how oxygen is mostly bound to hemoglobin, 98 to 99% of it, and only a very small 1 to 2% is dissolved in blood. The similar scenario is true for CO2, where as the dissolved gas in plasma, that only accounts for 10% of CO2 in blood. CO2 can bind to hemoglobin, and particularly deoxyhemoglobin. It has a higher affinity, and so that will also account for a significant portion of CO2 in blood will be that it's bound to hemoglobin. But most of CO2 in blood, 60%, will be as bicarbonate ion. And this set of chemical reactions right here is important for you to commit to memory, because we're going to be talking about it for the rest of our time studying the respiratory system, and then we're going to come back to it when we talk about the kidneys and their regulation of acid-base balance. So the reason why CO2 gets converted to bicarbonate is because of these reactions, where water and CO2 can combine through the action of carbonic anhydrase, an enzyme that helps convert water and CO2 to carbonic acid, which will then dissociate into bicarbonate and a proton. So that means that, and we'll see this in a figure in a moment, when the blood comes to the tissues and CO2 enters the blood, that is going to force these reactions to the right, because we're increasing the amount of CO2, which means that we produce more bicarbonate and more protons. So you can keep that in mind, that whatever happens to CO2 is going to cause an increase in bicarbonate and an increase in protons. Similarly, if we have an increase in protons, then we're going to move the set of reactions this way, and we're going to have increased CO2. So we're going to talk about this more and more, but keep that in mind, that these reactions are going to be present and affecting the amount of CO2 versus the amount of acid, therefore the pH, throughout the rest of our discussions. So again, this is a view of what's going to happen, where in the tissues we are going to have a pressure of CO2, let's say, of about 46, and but in the blood only a pressure of 40. So we're going to have a gradient for CO2 to diffuse into the blood. Some of it will just stay dissolved in the blood. We'll also have a gradient for CO2 to enter the red blood cell. Again, some of it will be able to be dissolved in the red blood cell. Some of it will bind to to hemoglobin, and then a large portion of it, about 60% of it, will be converted to bicarbonate. Then when we get to the lung, we're going to have a gradient where CO2 is higher in the blood than it is in the lung, and so CO2 is going to diffuse to the lung. That's going to cause CO2 to diffuse out of the red blood cell and cause it to also be removed from hemoglobin, and then also cause bicarbonate and protons to combine to form H2O and CO2, so that the CO2 can be removed through and diffused into the alveolus. We're going to now switch gears a little bit and talk about what's called VQ mismatch, ventilation and perfusion. So the V is for ventilation, and the Q is for perfusion. And the idea that even though we've been talking about the lung as if the whole length of it is the same, that actually it is not. Mostly just because of gravity. So let's consider this, where we're looking at, depending on where we are in the lung, whether we're in the bottom of the lung or the top of the lung, that both ventilation and blood flow, or Q, and the perfusion changes. And what that means in terms of, unless they are perfectly matched, then we're not going to have perfect exchange. So let's consider ventilation first, where we know that we have our lung, and it's really kind of hanging in the chest wall. And so what that means is that the top of the lung is stretched more than the bottom of the lung because it's got the rest of the lung hanging from it. And what that affects is the compliance, where you can see with this slinky, the top is already stretched, so it's lost some of its compliance, whereas the bottom of the lung, since it's just hanging there, has increased compliance. It's much more distensible. And so because of that, that means that the ventilation is decreased at the top of the lung and increased at the bottom of the lung. So at the bottom of the lung, where there's increased compliance, that we have increased ventilation. So that's what we see on this graph, where ventilation is greatest at the bottom of the lung. It's not a huge effect with ventilation, but it is an effect. With blood flow, we see a larger effect. The slope of the line is much more steep, but it's still in the same direction, where at the bottom of the lung, we have greatest blood flow. There's a couple of reasons for that. One is, again, due to gravity and the fact that the bottom of the lung is below the heart. So blood is going to tend to kind of, not necessarily pool, but be more present in larger flow amounts at the bottom of the lung. The other issue is that we've already looked at how the lung tissue itself is going to change from the bottom to the top. How that these, since they're more stretched, the top of the lung, the alveoli are more stretched, which is why their compliance is less. That also means that the capillaries between the alveoli are more compressed. And so that's another effect of really gravity on the lung, is this compressed vasculature in the top of the lung, which again is what makes such a dramatic difference in the blood flow of the bottom of the lung versus the top of the lung. So both ventilation and perfusion are increased at the bottom of the lung, but you see, because the slope of the ventilation is not very steep and the slope of the blood flow is steeper, that the lines cross, which means that the VQ ratio is greater than 1 at the top of the lung, because ventilation is greater than perfusion, but that the VQ ratio is less than 1 at the base, because of this fact that now blood flow is increased over ventilation. So the VQ ratio swaps from being less than 1 to more than 1 when you go from the top to the bottom, but in both cases, blood flow and ventilation are greater at the bottom of the lung. And this we're talking about a normal lung, so in all of us. And it ends up meaning that our VQ ratio for kind of the lung in general is 0.8. It's not a perfect machine in terms of VQ mismatch. Now, there are also many disease processes that can affect VQ mismatch even more dramatically, and that's what this talks about. Where, for instance, we could have decreased blood flow. So it could be because we have a blood clot or an air bubble in a portion of, in a blood vessel that's leading to a portion of the lung. So when that happens, then the pressure of carbon dioxide in the alveolus is going to decrease. Because remember, if blood can't flow to that portion of the lung, then CO2 is not going to be delivered, and there's really low CO2 in the atmosphere. So without that CO2 coming from the blood, the pressure of CO2 will be low. So the body senses this and says, okay, for some reason I'm not receiving blood flow. What I'm going to do is cause bronchoconstriction, which doesn't make so much sense unless you think about the fact that then that allows the air that was going to that part of the lung to go to a different part of the lung where it can actually be used. There's no point in wasting that air that's coming in to that part of the lung if it's not getting exposed to blood. And so instead, it gets diverted to another part of the lung that is healthy. Similar thing happens if we have decreased airflow. So let's say you inhale something that blocks one of your bronchioles so that a whole portion, small portion of the lung cannot get any fresh air. That will result in the pressure of oxygen in the capillaries that feed that part of the lung to decrease. And so again, the body says, for some reason we're not getting ventilation to this part of the lung. That's just a waste, so let's now have vasoconstriction, which will allow the blood to go to and be diverted to a different part of the lung where there is proper ventilation. And this is very interesting because you've already heard about in the cardiovascular system from Dr. Jacoy how if the pressure of oxygen goes down, then you're going to get dilation of the vessels to try to increase blood flow. And so here in the lung, because its function is different, we're getting an opposite effect, where low oxygen actually causes vasoconstriction. This system can also be a problem for people when we have situations like really high altitude, where now we've got basically the very similar case of decreased airflow because we're at the pressure of oxygen in the atmosphere is much lower. So the lung senses this by having because of a reduced pressure of oxygen in the capillaries. The problem is that's true for the whole lung because it's just the problem with the air that's being breathed, and that can cause really kind of universal vasoconstriction in the lung, which then can cause the pressure to increase so much that the capillaries start leaking and then cause massive pulmonary edema, which then is going to make the problem even worse in terms of trying to breathe because now we've increased the diffusion barrier. And so not only is now the oxygen is low in the atmosphere, and then what little is there is going to have much more difficult time diffusing into the blood. And so this is what happens in high altitude pulmonary edema when this VQ mismatch compensation goes wrong. And there's some people that are more susceptible to high altitude pulmonary edema, but it's really the response is based on this response to VQ mismatch. The problem comes when the whole lung responds in that way, and then if you have leaky capillaries. So we've talked about how we have carbon dioxide. It's soluble in blood, so it's not going to need a carrier like oxygen needs hemoglobin. But and it also means that carbon dioxide is going to be very proportional to minute ventilation, whereas oxygen is going to be less proportional because you've got the effect of how much oxygen is on hemoglobin, which does not change linearly with the change in pressure in of oxygen in the blood. The arterial blood gases are going to give a monitor for the adequacy of perfusion. And even in a normal lung function, we're going to have to worry about trying to match ventilation and perfusion, and it's not going to be perfect. And we have compensatory systems built in to try to keep ventilation and perfusion as close as possible.